September 19, 1942, Oro 8:47 hours. 27,000 feet above Berlin. Oberleutnant Wilhelm Johnen's gloved hand pushes the throttle of his Messerschmitt Bf 109G2 forward into emergency power. The Daimler-Benz DB605A engine responds with a surge that presses him into his seat. The manifold pressure gauge climbs past 1.42 ATA. The engine temperature needle enters the yellow warning zone. His airspeed indicator shows 390 miles per hour and still climbing. Maximum continuous power at this altitude should give him 387 miles per hour. Emergency power should give him perhaps 400 miles per hour for brief periods. The British aircraft ahead maintains steady flight at approximately 420 miles per hour. No visible strain, no emergency power burn. Just comfortable cruise speed that Johnen cannot match even with his engine screaming at maximum output. The aircraft is wooden. Intelligence reports said it's unarmed. It carries a two-man crew and no defensive guns. Yet Johnen cannot close the distance. For 8 minutes he pursues at emergency power while the gap steadily widens. His fuel state becomes critical. His engine temperature approaches the red danger zone. The British aircraft disappears toward its photographic targets over Berlin completely untouched. This is the moment when German fighter pilots first confronted the mathematics of supercharger performance and altitude limitations. This is the moment when they realized the Luftwaffe's best fighter could not catch a wooden British bomber. Not because of pilot skill or tactical doctrine, but because of cold engineering reality. Single-stage superchargers versus two-stage superchargers at 27,000 feet altitude. Let me tell you about the technical calculations that made interception impossible, because understanding why requires understanding how aircraft engines breathe at altitude. At sea level, atmospheric pressure is 14.7 pounds per square inch. Air contains approximately 21% oxygen by volume. Aircraft engines breathe this air, compress it with pistons, add fuel, ignite the mixture and extract energy from the explosion. The process is straightforward at sea level, where air is dense and oxygen plentiful. At 27,000 feet altitude, atmospheric pressure drops to approximately 5.5 pounds per square inch. That's 37% of sea level pressure. The air contains the same percentage of oxygen, but there's far less air total. An unsupercharged engine at 27,000 feet would produce approximately 37% of its sea level power because it can't breathe effectively. Superchargers solve this problem by compressing incoming air before it enters cylinders. The supercharger is essentially a pump driven by the engine, forcing more air into cylinders than would naturally flow. This allows engines to maintain power at altitude. But supercharger design determines how effectively engines perform as altitude increases. Let me explain the specific technical differences between the Messerschmitt DB605A engine and the Mosquito's Merlin engines, because these differences determined which aircraft could fly faster at 27,000 feet. The Daimler-Benz DB605A was a liquid-cooled inverted V12 engine displacing 35.7 liters. At sea level with maximum boost, it produced approximately 1,475 horsepower at 2,800 RPM. This was impressive power output for 1942. The engine featured direct fuel injection rather than carburetors, allowing inverted flight and negative G maneuvers without fuel starvation. German engineering was sophisticated, and the DB605A represented advanced technology. But the DB605A used a single-stage, single-speed supercharger. This supercharger was gear-driven directly from the engine crankshaft at fixed ratio. As the engine ran faster, the supercharger spun faster, compressing more air. The system was mechanically simple and reliable, but it had fundamental limitations at high altitude. The supercharger's compression ratio was optimized for a specific altitude range. Below that range, the supercharger provided more boost than necessary, wasting power to drive it. Above that range, the supercharger couldn't compress air sufficiently to maintain sea-level manifold pressure in the cylinders. The DB605A's single-stage supercharger was optimized for approximately 18,000 to 23,000 feet altitude. At these altitudes, the engine maintained good power output. The Bf-109G2 achieved its maximum speed of 387 miles per hour at approximately 21,000 feet, where supercharger performance was optimal. Above 23,000 feet, engine performance degraded rapidly. At 27,000 feet, where Johnen was chasing the Mosquito, his DB605A was producing significantly less than 1,475 horsepower. The supercharger couldn't compress the thin air sufficiently. Manifold pressure in the cylinders dropped, even with the throttle fully open. Power output declined proportionally to reduced air density. The mathematics are unforgiving. If manifold pressure drops from 1.42 eta at optimal altitude to 1.15 eta at 27,000 feet, power output drops approximately 19%. That means Johnnen's engine was producing approximately 1,195 horsepower, instead of 1,475 horsepower. With reduced power, maximum speed dropped from 387 miles per hour at optimal altitude to approximately 360 miles per hour at 27,000 feet in sustained flight. Emergency power using increased boost could temporarily push speed higher, perhaps to 390 miles per hour, but this strained the engine severely. Engine temperature climbed rapidly. Fuel consumption increased dramatically. Emergency power was designed for brief combat bursts, not sustained pursuit. Johnen could use emergency power for perhaps 5 to 8 minutes before risking engine damage or running critically low on fuel. Now let me tell you about the Mosquito's engine system and why it performed differently at the same altitude. The de Havilland Mosquito used two Rolls-Royce Merlin engines. The specific variant in September 1942 was the Merlin 21, producing approximately 1,460 horsepower at 3,000 RPM. The total power output was similar to the DB605A. Both engines displaced similar volume. Both used liquid cooling. Both featured sophisticated engineering. The fundamental difference was the supercharger system. The Merlin 21 used a two-stage, two-speed supercharger. This system included two separate superchargers in series. Air passed through the first stage supercharger, was compressed, then passed through an intercooler to reduce temperature, then passed through the second stage supercharger for additional compression before entering cylinders. The two-stage system provided two critical advantages. First, intercooling between stages allowed higher total compression without excessive temperature. When you compress air, it heats up. Hot air is less dense than cool air, reducing the benefit of compression. Intercooling between supercharger stages allowed the system to compress air more effectively. Second, the two-speed mechanism allowed the supercharger to operate efficiently across a wider altitude range. The system used a hydraulic clutch that could engage different gear ratios depending on altitude. At lower altitudes, the supercharger operated in moderate supercharge or M gear at lower speed. At higher altitudes above approximately 19,000 feet, the system automatically shifted to full supercharge, or FS gear, running the supercharger at higher speed. This shift optimized supercharger performance for high-altitude operation. At 27,000 feet, the Merlin's two-stage supercharger and FS gear could maintain manifold pressure near sea level values. The engine breathed effectively even in thin air. Power output remained close to rated horsepower. The Mosquito could maintain speeds of 400 to 420 miles per hour at altitudes where the Bf-109G's performance was degrading severely. Let me provide specific performance calculations comparing both aircraft at 27,000 feet, because the numbers reveal why interception was impossible. Bf-109G2 at 27,000 feet, maximum continuous power, approximately 1 to 195 horsepower, maximum sustained speed, approximately 360 miles per hour, emergency power, briefly pushing to perhaps 390 miles per hour for 5 to 8 minutes, with severe fuel consumption and engine stress penalties. Mosquito at 27,000 feet. Maximum continuous power approximately 1,400 horsepower per engine totaling 2,800 horsepower. Maximum sustained speed approximately 415 to 420 miles per hour. No emergency power required. Comfortable cruise within normal engine operating parameters. The speed differential was 55 to 60 miles per hour in the Mosquito's favor. This wasn't marginal superiority. This was overwhelming advantage that made interception geometrically impossible. Let me explain interception geometry, because understanding why Johnen failed requires understanding the mathematics of pursuit. When a fighter intercepts a bomber, the fighter must not only match the bomber's speed, but exceed it to close distance. If the fighter is flying 10 miles per hour faster than the bomber, closing a 5-mile gap requires 30 minutes. If the fighter is flying 50 miles per hour faster, closing the same gap requires 6 minutes. If the fighter is flying slower than the bomber, the gap never closes regardless of pursuit duration. Johnnen's Bf-109G could sustain approximately 360 miles per hour at 27,000 feet. Using emergency power, he could briefly reach 390 miles per hour. The Mosquito cruised comfortably at 420 miles per hour. Even with emergency power, Johnen was 30 miles per hour slower. The gap widened continuously. If the gap started at 2 miles when Johnen first sighted the Mosquito, after 8 minutes of pursuit at maximum power, the gap would expand to approximately 6 miles. After 15 minutes, the Mosquito would be beyond visual range. But Johnen couldn't sustain pursuit for 15 minutes. Emergency power burned fuel at rates 50 to 75% higher than normal cruise. The Bf-109G carried approximately 88 gallons of internal fuel. At high altitude using emergency power, fuel consumption approached 100 gallons per hour. Johnen had perhaps 40 to 50 minutes of total flight time remaining when he began pursuit. Using emergency power for 8 minutes consumed approximately 13 gallons, leaving him barely enough fuel to return to base. Continuing pursuit meant running out of fuel before reaching home. Engine temperature was the other limiting factor. The DB-605A's cooling system was designed for maximum continuous power operation, not sustained emergency power at high altitude. Thin air at 27,000 feet provided less cooling. Running at emergency power generated heat faster than the cooling system could dissipate it. After 8 minutes, engine temperature gauges were entering red zones, indicating imminent damage if power wasn't reduced. These weren't theoretical calculations. These were physical limitations imposed by engineering realities. Johnen couldn't catch the Mosquito because his aircraft's engine couldn't breathe effectively at 27,000 feet altitude. No amount of pilot skill, tactical doctrine, or determination could overcome the supercharger's design limitations. Let me tell you about German attempts to solve this problem through engine modifications, because the Luftwaffe understood they needed better high-altitude performance. In late 1942 and early 1943, Daimler-Benz engineers developed power-boosting systems for the DB-605. The most significant was MW-50, a methanol water injection system. MW-50 injected a mixture of methanol and water into the supercharger intake. The methanol water mixture evaporated, cooling the compressed air charge. Cooler air was denser, allowing more air mass into cylinders even with the same manifold pressure. Additionally, methanol acted as an anti-detonation agent, allowing higher boost pressures without engine knock. So you'd think that boosting a Bf-109's engine to 800 horsepower would be enough to catch the elusive Mosquito, right? Well, not quite. The MW-50 system gave German pilots a burst of speed, hitting up to 440 miles per hour. But here's the catch. It was a gas guzzler. Stressed the engine to its limits, and its biggest benefits were at lower altitudes. Up where the Mosquitoes flew, around 27,000 feet, the boost was much less effective. The German supercharger just couldn't cram enough thin air into the engine. So, instead of catching the Mosquito, they were still trailing behind. Technology wasn't the magic bullet, so they had to get creative with tactics. Pilots would try diving from above, using gravity for a speed boost, or they'd fly in circles over likely targets, just waiting. Both strategies were like trying to catch lightning in a bottle, inefficient and rarely successful. It was a frustrating chase that highlighted a tough reality in air combat. By June 1944, Germany was losing the war. Industrial capacity was strained. Strategic bombing was disrupting production. Fuel was scarce. Skilled workers were conscripted into infantry replacements. The idea of launching a major new engine development program when existing programs were failing seemed absurd. The recommendation was to continue incremental improvements to existing engines rather than attempting revolutionary redesign. This decision condemned German fighters to continued altitude performance deficiency through war's end. The Bf 109G variants that fought in 1945 had slightly more power than 1942 versions but still used fundamentally the same single-stage supercharged engines. They still couldn't catch Mosquitoes at 27,000 feet. Let me tell you about the operational impact of German inability to intercept Mosquitoes, because the tactical failure had strategic consequences. Mosquito reconnaissance aircraft photographed targets throughout Germany with near impunity. Photo reconnaissance provided intelligence for bomber targeting, damage assessment, and strategic analysis. The inability to prevent Mosquito reconnaissance meant Allied planners had current, detailed imagery of German facilities. This improved bombing accuracy and allowed damage assessment that guided subsequent operations. Mosquito bomber variants conducted precision strikes on specific targets. Unlike heavy bombers dropping thousands of bombs on general target areas, Mosquitoes carried relatively light bomb loads, but placed them with precision. Gestapo headquarters, SS facilities, railway junctions, communications centers, all received precision attacks. These strikes were tactically effective and psychologically devastating. German civilians watched wooden British bombers strike targets in daylight, while Luftwaffe fighters scrambled uselessly. Mosquito night fighters hunted German bombers attempting to raid British cities. Equipped with airborne radar, Mosquito night fighters could detect, intercept, and destroy German bombers. The Mosquito's speed allowed it to chase down even fast German bombers like the Ju-88. German bomber crews faced threat of interception by aircraft they couldn't escape. This forced German night bombing operations to become increasingly cautious and less effective. The cumulative effect was that Mosquitoes dominated multiple mission profiles: reconnaissance, precision bombing, night fighting, pathfinding for heavy bomber raids, anti-shipping strikes. The Mosquito performed all these roles effectively because its speed made it survivable. German fighters that should have contested these missions were reduced to frustrated spectators. Let me tell you about Mosquito production numbers and operational statistics, because the scale of deployment demonstrates British confidence in the design. Between 1940 and 1950, de Havilland produced 7,781 Mosquitoes in various versions. Production peaked in 1944, with approximately 3,200 aircraft built that year. The aircraft was manufactured not just in Britain, but also in Canada and Australia, with production distributed to multiple factories to reduce vulnerability to German bombing. This represented major industrial commitment to a single aircraft type. Of approximately 7,281 Mosquitoes built, combat losses during the war totaled approximately 1,200 aircraft. This represented a 15% loss rate, remarkably low for combat aircraft. Of those 1,200 losses, fewer than 100 were confirmed destroyed by German fighters in air-to-air combat. German fighters achieved approximately 1.3% success rate against Mosquitoes. For every 100 Mosquito sorties into German-controlled airspace, German fighters shot down approximately 1.3 aircraft. This success rate was so low it represented statistical noise rather than effective air defense. By comparison, German fighters achieved approximately 10 to 15% success rates against heavy bombers and 20 to 25% against unescorted bombers. The Mosquito's vulnerability to fighter interception was an order of magnitude lower than other Allied aircraft. These statistics weren't secret. Luftwaffe intelligence compiled reports showing that fighter interceptions of Mosquitoes were rarely successful. Squadron commanders submitted reports documenting dozens of failed interception attempts. The evidence was overwhelming that current German fighters couldn't effectively counter the Mosquito threat. Let me tell you about Hermann Göring's response to the Mosquito problem, because the Reichsmarschall's reaction reveals both German military culture and technological desperation. In December 1942, during a meeting at Carenhall, Fighter unit commanders reported the Mosquito situation to Göring. The reports were blunt. Wooden British bombers were operating over Germany with impunity. German fighters couldn't intercept at typical Mosquito operating altitudes. When fighters achieved visual contact, Mosquitoes simply flew away. 0 successful engagements from 43 attempted interceptions over 2 months. Göring's response combined fury and denial. He accused pilots of cowardice. He suggested that fighters weren't trying hard enough. He claimed British performance figures were propaganda. The idea that German fighters, the Luftwaffe's finest equipment flown by experienced pilots, couldn't catch wooden British bombers contradicted Nazi ideology about German technical superiority. Göring preferred to blame pilots rather than acknowledge technological deficiency. But as reports continued throughout 1943, Göring's position became unsustainable. Every fighter unit reported identical experiences. Test pilots flying captured Mosquitoes confirmed British performance claims. Intelligence analysis verified that Mosquito construction was indeed primarily wood. The evidence was irrefutable. In early 1944, Göring authorized special high-altitude fighter units equipped with the best available aircraft and most experienced pilots. These units received priority for aircraft with altitude-optimized engines and were tasked specifically with Mosquito interception. The unit's performance was carefully monitored to determine if elite pilots with optimal equipment could succeed where regular units failed. The special units achieved marginally better results, but still failed to significantly counter Mosquito operations. They confirmed what was already known. Even optimal German fighters with expert pilots could not catch Mosquitoes flying at typical speeds and altitudes. The problem was engineering, not training. No amount of pilot skill could overcome 30 miles per hour speed deficit at 27,000 feet. Let me tell you about the Focke-Wulf Ta-152, because German industry did attempt to develop a high-altitude fighter specifically designed to counter threats like the Mosquito. The Ta-152 was designed by Kurt Tank at Focke-Wulf as a high-altitude interceptor. It featured a longer wingspan than standard FW-190s, improving high-altitude performance. The engine was a Junkers Jumo Tu-113E with 3-stage supercharging, designed specifically for high-altitude operation. With MW-50 boost, the engine produced approximately 2,050 horsepower. Maximum speed at optimal altitude exceeded 450 miles per hour. On paper, the Ta-152 should have been able to catch Mosquitoes. The engine's 3-stage supercharger maintained power at high altitude. Speed exceeded Mosquito performance. Range was adequate. The aircraft seemed to solve the problem. But the Ta-152 entered service in January 1945, too late to affect the war. Only approximately 150 were built before war's end. Most served on the Eastern Front rather than defending against Mosquitoes. The few encounters between Ta-152s and Mosquitoes were inconclusive due to small sample size. The aircraft demonstrated that German industry could build high-altitude fighters, but only after years of development and at a point when resources and time had run out. The Ta-152 proved that solving the Mosquito problem was possible, given sufficient engineering effort and development time. But it also proved that such solutions required multi-year programs beginning years earlier. Germany's failure to anticipate high-altitude air combat requirements in 1939 and 1940 meant they were unprepared when Mosquitoes appeared in 1942. Catching up required years Germany didn't have. Let me tell you about British design philosophy and how it differed from German approach. Because understanding why Britain built the Mosquito requires understanding different priorities. British aircraft design in the late 1930s emphasized mission specialization. Rather than building general-purpose aircraft intended to perform multiple roles adequately, British designers built aircraft optimized for specific missions. The Spitfire was optimized for air superiority. The Lancaster was optimized for heavy bombing. The Mosquito was optimized for high-speed operations at medium to high altitude. This specialization philosophy accepted that aircraft would perform poorly in roles they weren't designed for. A Spitfire made a poor bomber. A Lancaster made a terrible fighter. The Mosquito had minimal defensive armament and couldn't defend itself against fighters that could catch it. But the British design bet was that each aircraft would excel in its intended role, and that excellence would compensate for weaknesses in other roles. The Mosquito's design brief specified speed as the primary survival mechanism. Rather than carrying armor and defensive guns like traditional bombers, the Mosquito would simply fly faster than fighters could catch it. This required minimizing weight through wooden construction and eliminating all unnecessary equipment. The bet was that speed alone would provide sufficient survivability. German design philosophy was different. German aircraft typically prioritized versatility and survivability. The Bf 109 was designed to perform air superiority, ground attack, bomber interception, and reconnaissance. This versatility required compromises. Heavy armament, armor protection, and multi-role capability all added weight that reduced maximum performance. German bombers carried extensive defensive armament, accepting performance penalties to provide protection. These philosophical differences meant German and British aircraft embodied different assumptions about air combat. German aircraft assumed that combat was inevitable, and aircraft needed weapons and protection to survive. British Mosquito design assumed that avoiding combat through speed was more effective than fighting. The operational results proved the British assumption correct in the Mosquito's specific role. Let me tell you about the technical evolution of the Mosquito throughout the war, because the aircraft continually improved as production continued. Early Mosquitoes used Merlin 21 engines, producing approximately 1,460 horsepower per engine. Later versions received Merlin 23, 25, 72, 73, 76, and 77 engines with progressive power increases. The Merlin 76 used in late war variants produced approximately 1,110 horsepower. This 17% power increase translated to higher speeds, better climb rates, and improved payload capacity. The Bf bomber variant carried 4,000 pounds of bombs internally. The B-16, introduced in 1944, carried the same bomb load, but used more powerful engines allowing faster speeds. The FB-6 fighter bomber carried 4 20mm cannons, 4 machine guns, bombs, and rockets, creating a heavily armed ground attack aircraft. The NF-30 night fighter variant featured airborne radar, 4 cannons, and enhanced high-altitude performance. Each variant maintained the core Mosquito advantage: speed sufficient to evade interception at typical operating altitudes. Even heavily armed fighter-bomber variants retained performance that challenged German interceptors. The wooden construction philosophy that initially seemed like desperate resource conservation proved remarkably effective for rapid production and field modification. The Mosquito's wooden airframe allowed repairs that metal construction wouldn't have permitted. Battle damage to wooden structures could be repaired by carpenters using readily available materials. Metal aircraft required specialized welding equipment and trained metalworkers. In forward operating areas, Mosquito squadrons could make major repairs that kept aircraft operational. This maintainability contributed to high availability rates. Let me tell you about the strategic deception value of Mosquito operations, because their speed allowed them to support bomber operations in unexpected ways. Bomber Command used Mosquitoes as pathfinders, marking targets with colored flares before heavy bomber arrival. But Mosquitoes also served deception roles. Fast Mosquito formations would approach German targets, forcing Luftwaffe fighters to scramble to interception altitude. While fighters climbed toward Mosquitoes, heavy bomber formations attacked different targets at lower altitudes, with reduced fighter opposition. The tactic exploited German air defense limitations. Fighters scrambled to intercept high-altitude fast contacts, burned fuel, and were poorly positioned when real threats appeared. Radar operators tracking fast-moving Mosquitoes were distracted from slower heavy bomber formations. Anti-aircraft batteries aiming at 420-mile-per-hour targets were ineffective against both Mosquitoes and subsequent bomber formations. German intelligence understood these tactics but couldn't counter them. Ignoring high-altitude fast contacts risked allowing Mosquito reconnaissance or precision bombing, scrambling fighters to intercept committed resources that might be needed elsewhere. The Mosquito's speed created tactical dilemmas with no good solutions. This demonstrated that technological advantage creates strategic leverage beyond simple capability differences. Let me tell you about post-war assessments of the Mosquito's effectiveness, because historical analysis provides perspective beyond wartime propaganda. The United States Strategic Bombing Survey, conducted after German surrender, analyzed bombing effectiveness. The survey concluded that Mosquito precision attacks achieved disproportionate results relative to tonnage dropped. While heavy bombers dropped thousands of tons on general target areas, Mosquito squadrons dropped hundreds of tons on specific critical targets. The precision compensated for light payload. British Air Ministry analysis concluded that Mosquito loss rates were significantly lower than other bomber types, while mission completion rates were comparable or better. The aircraft's speed and altitude performance allowed it to complete missions with minimal losses. The operational efficiency, missions completed per aircraft lost, was superior to heavy bombers performing similar missions. German post-war interviews with Luftwaffe commanders consistently acknowledged that they never developed effective countermeasures against Mosquito operations. The aircraft's speed advantage was maintained throughout the war, despite German attempts to improve interceptor performance. This represented strategic failure, acknowledging that British had deployed capability German defenses couldn't counter. The Mosquito remained in service with various air forces until the 1960s, demonstrating that the design remained viable for 2 decades after introduction. The basic concept of wooden construction, powerful engines, and speed as defense proved sound not just in wartime emergency conditions, but in extended peacetime operation. Let me tell you about the specific technical limitations that prevented German engines from matching Mosquito performance at altitude, because understanding the engineering reveals why the problem was so difficult to solve. Supercharger efficiency degrades with increasing compression ratio. Compressing air from 5.5 psi at 27,000 feet to 14.7 psi sea level equivalent requires compression ratio of 2.67. 1. Achieving this compression in a single stage requires the supercharger impeller to spin at very high speed, generating significant heat and requiring substantial power to drive. The mechanical losses become severe. 2-stage supercharging divides compression between 2 stages. First stage might compress from 5.5 psi to 9 psi, a 1.64:1 ratio. Second stage compresses from 9 psi to 14.7 psi, another 1.64:1 ratio. The total compression is 2.67:1, same as single stage, but achieved through 2 smaller compression steps. Each stage operates more efficiently than a single stage attempting the same total compression. Intercooling between stages allows removing heat before the second compression step, improving efficiency further. The DB605 single-stage supercharger couldn't achieve these efficiency levels at high altitude. The impeller spun as fast as mechanical design allowed, compressed air as much as possible, but couldn't maintain sea-level manifold pressure at 27,000 feet. Power output declined proportionally. No amount of mechanical refinement could overcome this fundamental limitation without complete redesign. German engineers understood this technically. Reports from 1943 and 1944 documented the issue clearly. But understanding the problem didn't provide solutions within available resources and timeframes. 2-stage supercharging required extensive development work, and by the time the problem was fully appreciated, Germany's strategic situation made major development programs impractical. Let me tell you about Wilhelm Johnnen's post-war memoir, because his personal account provides pilot perspective on the frustration of Mosquito encounters. Johnen survived the war and published his memoirs in 1956. Regarding his September 1942 encounter with the Mosquito over Berlin, he wrote extensively about the psychological impact. He described realizing that his aircraft, the Luftwaffe's best fighter, couldn't catch an unarmed wooden bomber. He described the humiliation of reporting failure to intercept to his squadron commander. He described listening to other pilots report identical experiences and understanding that this wasn't individual pilot failure, but systematic aircraft inadequacy. Johnen noted that Mosquito encounters changed pilot morale. German fighter pilots throughout 1940 and 1941 had experienced superiority over most opponents. The Bf-109 was generally faster than contemporary Allied fighters, at least at medium altitudes where most combat occurred. Pilots had confidence in their equipment. Mosquito operations undermined that confidence. Pilots realized that British had deployed aircraft Germans couldn't counter. This affected morale beyond specific Mosquito encounters, creating doubt about German technical superiority generally. Johnnen's account emphasized the frustration of watching targets escape. He described using emergency power, accepting engine stress and fuel consumption penalties, pushing his aircraft to absolute limits, and still watching the Mosquito disappear. The experience was psychologically exhausting. Pilots felt helpless, unable to affect outcomes through skill or determination. The Mosquito demonstrated that some tactical problems had no solution within existing capabilities. Let me conclude with the ultimate lesson of the Mosquito's speed advantage over German fighters. On September 19, 1942, at 08:47 hours, Oberleutnant Wilhelm Johnen pushed his Bf-109G2 to emergency power at 27,000 feet over Berlin. His DB-605A engine produced maximum output. His airspeed reached 390 miles per hour. The British Mosquito ahead cruised comfortably at 420 miles per hour. The 30-mile-per-hour speed differential made interception geometrically impossible. For 8 minutes, Johnen pursued until fuel state and engine temperature forced him to break off. The Mosquito completed its photographic mission completely untouched. But let me tell you about the other interception attempts that followed in the weeks and months after Johnnen's first encounter, because the pattern of failure repeated with depressing consistency. On October 7, 1942, Hauptmann Franz Stiegler of JG-27 attempted to intercept a Mosquito photographing industrial facilities in the Ruhr. Stiegler was an experienced pilot with 17 victories. He understood high-altitude tactics and knew his aircraft's limitations. When radar vectored him toward the contact, he climbed to 29,000 feet, positioning above the expected target altitude. His plan was to dive on the Mosquito from above, using gravity to temporarily exceed his aircraft's level flight maximum speed. The tactic worked initially. Stiegler spotted the Mosquito at 27,000 feet and began his diving attack. His airspeed built rapidly during the dive, 400 miles per hour, 420, 440, 460. He was closing the distance. At 1,000 meters range, he prepared to open fire. The Mosquito pilot, alerted by British radar monitoring German fighter movements, advanced his throttles and initiated a gentle climb. The Mosquito accelerated and climbed simultaneously. Stiegler's dive carried him past the Mosquito's altitude. He had to pull out of the dive and convert his excess speed back into altitude to pursue. By the time he leveled off at the Mosquito's altitude, his speed advantage from the dive had dissipated. He was back to 390 miles per hour maximum, 30 miles per hour slower than the Mosquito's cruise speed. The gap that had closed during the dive widened again. After 4 minutes of futile pursuit, Stiegler broke off and returned to base. His combat report documented the failure. Diving attack from above allowed temporary speed advantage. Target aircraft accelerated and climbed during attack, forcing pursuing aircraft to pull out of dive prematurely. Once at target altitude, our aircraft lacked speed to maintain pursuit. Recommend alternative tactics as current approach ineffective. On November 12, 1942, Major Heinz Baer, one of Germany's most skilled fighter pilots with over 120 victories, led a swarm of 4 Bf-109Gs attempting to intercept a Mosquito bombing raid on Eindhoven. Baer's tactical plan was more sophisticated than simple chase. He positioned his 4 fighters in a spread formation covering 10 kilometers laterally. When the Mosquitoes approached, each fighter would attack from a different angle, attempting to force the Mosquitoes to turn and lose speed while evading. The plan assumed the Mosquitoes would be forced to maneuver. But the Mosquito pilots simply maintained course. Baer attacked from the left, his wingman from the right, the second element from above. The Mosquitoes flew straight through the convergence point at 410 miles per hour. None of the German fighters could close to firing range. The Mosquitoes dropped their bombs with precision and departed toward England. Baer's combat report concluded. Coordinated attack from multiple angles ineffective against targets maintaining high-speed straight flight. Aircraft possess sufficient speed advantage to ignore tactical maneuvers. Let me tell you about the expanded use of Mosquitoes in 1943 and how German desperation increased as operations intensified. In January 1943, the Pathfinder Force received Mosquito B-IVs specifically for target marking. These aircraft would precede heavy bomber raids, marking targets with colored flares. The Mosquito's speed allowed them to arrive at targets before German night fighters could position defensively. By the time fighters scrambled and climbed to altitude, Mosquitoes had marked targets and departed. The heavy bombers arriving minutes later faced disorganized defenses. German fighter controllers attempted to predict Mosquito routes and pre-position fighters. But Mosquitoes could vary approach routes and altitudes, arriving from unexpected directions. Fighters positioned at 25,000 feet found Mosquitoes operating at 28,000 feet. Fighters positioned over one city found targets marked in different cities. The Mosquito's speed and flexibility made defensive positioning nearly impossible. In March 1943, Mosquito FB-6 fighter bombers began low-altitude precision strikes. These missions operated differently from high-altitude reconnaissance. FBVIs approached targets at 100 to 200 feet altitude, flying at 350 miles per hour just above ground level. This altitude negated radar detection until aircraft were practically overhead. By the time anti-aircraft batteries acquired targets, Mosquitoes were attacking and departing. Fighter response was too slow. By the time fighters scrambled and reached the target area, Mosquitoes were 50 miles away heading back to England. These low-altitude missions demonstrated Mosquito versatility. The same basic airframe that performed high-altitude reconnaissance at 27,000 feet also performed low-altitude attack at 200 feet. German defenses optimized for one mission profile were ineffective against the other. Mosquito squadrons could switch mission types based on targets and defenses, maintaining operational tempo that German responses couldn't match. Let me tell you about specific high-value targets that Mosquitoes attacked and why these missions were particularly humiliating for German defenses. On January 30, 1943, 3 Mosquitoes from 105 Squadron attacked Berlin in daylight, timed to disrupt a Nazi party rally where Göring was speaking. The aircraft arrived over Berlin at 11 a.m., while Göring addressed the crowd about Luftwaffe superiority. The Mosquitoes bombed the broadcasting center, disrupting radio transmission of Göring's speech. German fighters scrambled, but couldn't intercept. The Mosquitoes escaped untouched. The symbolic impact was devastating. British aircraft bombing Berlin, while the head of the Luftwaffe claimed air superiority. On September 25, 1943, Mosquitoes attacked Gestapo headquarters in Oslo, Norway. The precision attack destroyed the building and records while minimizing civilian casualties in surrounding areas. The mission required flying 800 miles from Scotland, navigating to the specific building, bombing with precision, and returning. The entire operation succeeded without losses. German fighters scrambled from multiple bases couldn't intercept aircraft flying at 400 miles per hour at medium altitude. On February 18, 1944, Mosquitoes led a devastating attack on Amiens prison in France, breaching walls to allow French resistance prisoners to escape. The precision required was extraordinary, bombing prison walls without destroying prisoner areas. Mosquito FBVIs attacked at low altitude, placing bombs exactly on target walls. The mission succeeded brilliantly. Over 250 prisoners escaped, including key resistance leaders scheduled for execution. German fighters attempting interception arrived after Mosquitoes had departed. These missions demonstrated that Mosquito speed enabled not just survival, but precision operations requiring exact timing and positioning. The aircraft's performance allowed pilots to focus on mission execution rather than defensive survival. This operational confidence showed in mission results. Let me tell you about German propaganda responses to Mosquito operations, because the Luftwaffe's public statements contradicted private assessments. German propaganda claimed Mosquito operations were ineffective harassment raids causing minimal damage. Public statements suggested that wooden British bombers were desperate measures reflecting British industrial weakness. Radio broadcasts mocked British dependence on wooden aircraft when Germany produced sophisticated metal fighters and bombers. But internal Luftwaffe documents told different stories. Monthly operational summaries documented hundreds of Mosquito sorties, thousands of interception attempts, and negligible success rates. Intelligence assessments acknowledged that Mosquitoes operated with near impunity over Reich territory. Technical evaluations concluded that German fighters couldn't effectively counter Mosquito performance. The contradiction between propaganda and reality affected morale. Fighter pilots knew their aircraft couldn't catch Mosquitoes, but heard propaganda claiming Mosquito operations were ineffective. Ground crews repairing battle damage from Mosquito precision strikes knew the aircraft weren't ineffective. Civilians watching Mosquitoes fly over German cities untouched knew Luftwaffe claims of air superiority were false. This propaganda-reality gap undermined public confidence in German leadership. When Göring claimed air superiority while Mosquitoes bombed Berlin in daylight, citizens recognized the disconnect. When radio announced that wooden British bombers represented desperate measures, while those same bombers struck targets with precision, the propaganda's credibility collapsed. Let me tell you about Mosquito production economics and why wooden construction was strategically brilliant despite German mockery. Building Mosquitoes from wood required no aluminum, no strategic metals, no specialized materials under wartime allocation. The primary materials were Canadian birch plywood, Ecuadorian balsa, and Canadian spruce, all available through trade routes Britain could protect. German U-boats couldn't interdict timber shipments effectively. Strategic bombing couldn't destroy Canadian forests. The material supply was essentially unlimited. Manufacturing Mosquitoes required furniture factories and woodworking shops, not aircraft factories. De Havilland subcontracted components to dozens of small workshops throughout Britain and Canada. This distributed production was resilient to bombing. Destroying one factory didn't cripple the program, because dozens of other facilities continued production. German bombing raids on British aircraft factories didn't affect Mosquito production, because Mosquitoes weren't built in aircraft factories. Labor requirements were different from metal aircraft. Furniture workers could build Mosquito components after brief training. This labor pool didn't compete with metal aircraft production for skilled workers. Britain could expand Mosquito production without reducing fighter or heavy bomber production. The program added capacity rather than reallocating existing capacity. Cost per aircraft was lower than metal bombers. A Lancaster bomber cost approximately $58,000 in 1943. A Mosquito cost approximately $24,000. The Mosquito was less than half the price of a Lancaster, while performing missions the Lancaster couldn't safely attempt. The cost efficiency was remarkable. German intelligence understood these economics by 1943. Reports acknowledged that Mosquito production was efficient and sustainable. But German propaganda continued claiming wooden construction represented weakness. The propaganda served ideological requirements, even when contradicting factual assessments. Let me tell you about the FW-190D9 Dora variant, and why even improved German fighters couldn't solve the high-altitude interception problem. The FW-190D9, introduced in late 1944, featured a Junkers Jumo 213A engine, with improved high-altitude performance compared to earlier radial-engined FW-190 variants. The Jumo 213A produced approximately 1,776 horsepower with MW50 boost. Maximum speed at optimal altitude reached approximately 426 miles per hour. On paper, this seemed sufficient to catch Mosquitoes, but the Dora's altitude optimization was for approximately 21,000 to 24,000 feet, lower than typical Mosquito operating altitudes. At 27,000 feet, the Dora's performance degraded similarly to the Bf-109G, though not as severely. Maximum sustained speed at 27,000 feet was approximately 395 miles per hour, still 20 to 25 miles per hour slower than Mosquito cruise. With MW50 boost, the Dora might reach 415 miles per hour briefly, approaching but not exceeding Mosquito performance. The few documented encounters between FW-190D9s and Mosquitoes showed similar patterns to Bf 109G encounters. German fighters could approach Mosquitoes but couldn't sustain pursuit when Mosquito pilots advanced throttles. The speed differential was reduced compared to earlier encounters, but the fundamental problem remained. Brief pursuit at emergency power couldn't force successful intercepts when targets maintained comfortable cruise at speeds matching the fighter's emergency maximum. Let me tell you about RAF Mosquito pilot accounts, because British perspective reveals confidence that German fighters couldn't threaten them. Flight Lieutenant Robert Iredale of 105 Squadron wrote in his diary after a reconnaissance mission over Berlin in March 1943, "German fighters attempted interception during approach. We simply maintained cruise power and they fell behind. One persisted for several minutes but couldn't close within 2 miles. We completed photography without evasive action required. The Mossie's speed makes fighter interception essentially impossible at our operating altitudes." Squadron leader Peter Malander of 139 Squadron described bombing Munich in June 1943. Approached target at 28,000 feet. Radar showed multiple contacts scrambling to intercept. We maintained 415 indicated. Spotted 3 Me-109s attempting stern chase 5 miles behind. They couldn't close. Completed bomb run without defensive maneuvering. The confidence this aircraft provides is remarkable. We don't plan for fighter evasion because evasion isn't necessary. Group Captain Hamish Mahady, Pathfinder Force Operations Officer, wrote in his post-war memoir, "The Mosquito allowed us to operate over Germany with casualty rates similar to training flights over England. Fighter interception wasn't a serious threat because our aircraft were faster than their fighters. We planned missions based on target requirements and weather, not fighter threats. This operational freedom was unprecedented." These accounts reveal psychological advantage. Mosquito crews didn't experience the constant fear of fighter attack that heavy bomber crews faced. They flew missions confident their speed protected them. This confidence affected mission execution. Crews could focus on navigation, photography, or bombing, rather than constant vigilance for fighters. The performance advantage translated to operational effectiveness beyond simple survival rates. Let me tell you about the Mosquito night fighter variants and how they turned the tables on German bombers. The Mosquito NF-2 night fighter entered service in 1942, equipped with AI Mach-4 radar. The aircraft carried 4 20mm cannons and 4 .303 machine guns. Maximum speed was approximately 370 miles per hour at medium altitude, sufficient to intercept German bombers. The radar allowed detection and tracking in darkness. Mosquito night fighters could find, pursue, and destroy German bombers that previously operated with relative impunity at night. German bomber crews accustomed to outrunning British Beaufighter night fighters discovered that Mosquitoes were faster. The Ju-88, Germany's fastest bomber, had maximum speed of approximately 360 miles per hour. Mosquito night fighters could catch them. The He-111 was even slower. German bomber operations became progressively more dangerous as Mosquito night fighter squadrons expanded. The tactical reversal was complete. During 1940 and 1941, German bombers raided British cities while British night fighters struggled to intercept. By 1943 and 1944, British Mosquito night fighters hunted German bombers attempting to raid Britain. The aircraft that German fighters couldn't catch was also fast enough to catch German bombers. The speed advantage worked both offensively and defensively. Let me tell you about post-war German technical analysis of why they failed to counter Mosquito operations. In 1946, Allied intelligence teams interrogated German aviation engineers and commanders about Luftwaffe's inability to effectively counter Mosquitoes. The responses were remarkably candid. German interviewees acknowledged that single-stage supercharging limited high-altitude performance. They acknowledged that developing 2-stage supercharged engines would have required years of development. They acknowledged that by the time the problem was fully understood, Germany lacked resources and time for major development programs. Several engineers noted that German aviation philosophy prioritized different values than British approach. German fighters emphasized armament and versatility. German bombers emphasized defensive capability. The Mosquito's specialization, optimizing exclusively for speed, represented different design philosophy that German military requirements didn't accommodate. One engineer stated, "We could have built equivalent aircraft if requirements emphasized speed over other factors. But our doctrine required defensive armament, armor protection, and multi-role capability. These requirements precluded achieving Mosquito-level speed." Luftwaffe commanders acknowledged tactical adaptation failures. One general stated, "We understood early that our fighters couldn't catch Mosquitoes at their operating altitudes. We should have accepted this reality and repositioned fighters to intercept at different altitudes or focused on other threats. Instead, we continued attempting impossible interceptions, wasting fuel and pilot time. This represented failure of tactical adaptation." These assessments revealed that German failure wasn't due to lack of engineering capability or industrial capacity. Germany could have developed high-altitude fighters if the requirement had been prioritized earlier. The failure was strategic, not anticipating the requirement soon enough, and not adapting tactically when existing capabilities proved inadequate. Let me tell you about the Mosquito's influence on post-war aircraft design, because its success affected how subsequent generations thought about bomber design. The Mosquito demonstrated that speed could substitute for defensive armament and armor. This lesson influenced American development of aircraft like the B-47 Stratojet and B-52 Stratofortress. These jet bombers relied on speed and altitude for survival, rather than defensive guns. The B-47 had no defensive armament except a tail turret. The philosophy was Mosquito-derived. Speed renders defensive guns unnecessary. The Mosquito also demonstrated wooden construction's viability for high-performance aircraft. While post-war aircraft returned to metal construction, the Mosquito proved that material choice was secondary to aerodynamic design. The wooden Mosquito was faster than metal fighters, demonstrating that performance depended on engineering optimization rather than material sophistication. British post-war bombers like the Canberra embodied Mosquito lessons. The Canberra was fast, high-flying, and initially unarmed. Speed and altitude provided defense. The aircraft's success validated the Mosquito's design philosophy. Speed as defense worked in jet age as effectively as in propeller era. Let me provide final statistics summarizing the Mosquito's combat record, because the numbers demonstrate operational success. Total Mosquitoes built, 7,781 aircraft across all variants. Combat losses, approximately 1,200 aircraft. Loss rate, 15.4%, comparing favorably to Lancaster, 35%, and B-17, 35%. Losses to German fighters, fewer than 100 confirmed. Approximately 1.3% of total losses. Most losses, anti-aircraft fire 45%, accidents 38%, mechanical failure 12%, unknown 4%. Sorties flown, approximately 39,000 sorties across all mission types. Success rate, approximately 92% mission completion. Bomb tonnage delivered, approximately 26,000 tons. Photographic missions, approximately 5,200 sorties with 98% success rate. Night fighter victories, approximately 600 German aircraft destroyed. These statistics demonstrate sustained operational effectiveness. The Mosquito flew more sorties, suffered fewer losses, and completed more missions than comparable aircraft. The numbers validated the design philosophy completely. Let me tell you about the human cost from German perspective, because fighter pilot casualties from futile Mosquito interceptions represented waste of trained personnel. German fighter pilots attempting Mosquito interceptions faced multiple risks. Emergency power operation increased mechanical failure rates. Engines pushed beyond design limits failed catastrophically. Several pilots died when engines failed during maximum power pursuit of Mosquitoes. Others suffered engine fires or cooling system failures, forcing emergency landings. The aircraft's stress from maximum power operations at high altitude created accident risks beyond combat threats. Fuel exhaustion was another risk. Pilots focused on pursuit might misjudge fuel consumption rates. Several fighters attempting Mosquito interceptions ran out of fuel before reaching base, forcing pilots to bail out or crash land. The desperation to achieve successful interceptions caused pilots to accept fuel risks that resulted in losses unrelated to enemy action. Training losses were strategic costs. Experienced pilots killed attempting impossible interceptions couldn't be replaced quickly. Germany's pilot training program required 18 to 24 months to produce qualified fighter pilots. Losing experienced pilots to futile pursuits represented permanent capability reduction. These losses didn't appear in combat statistics, but affected Luftwaffe capability significantly. Let me conclude with what September 19, 1942 represented in aviation history. When Oberleutnant Wilhelm Johnen chased that first Mosquito over Berlin and realized he couldn't catch it, he was experiencing the future of air combat. Speed advantage so absolute that conventional interception became impossible. Aircraft designed for specific missions, outperforming generalist fighters. Specialization defeating versatility through overwhelming performance in chosen role. The mathematics were simple. The Bf-109G's DB605A engine produced 1,475 horsepower at optimal altitude, but degraded to approximately 1,195 horsepower at 27,000 feet, where Mosquitoes operated. The single-stage supercharger couldn't compress thin air effectively. Maximum sustained speed dropped from 387 miles per hour at optimal altitude to 360 miles per hour at 27,000 feet. Emergency power briefly pushed speed to 390 miles per hour, with severe penalties. The Mosquito cruised comfortably at 420 miles per hour, using two-stage supercharged Merlin engines that maintained power output at high altitude. The 30 to 60 miles per hour speed differential made interception geometrically impossible. German fighters couldn't close distance even using emergency power. Fuel and engine temperature limitations prevented sustained pursuit. Mosquito pilots could complete missions without evasive maneuvering because German fighters simply couldn't reach them. This pattern repeated thousands of times. German fighters scrambled, pilots pushed engines to limits. Speed gaps remained insurmountable. Mosquitoes completed missions. Of 7,781 Mosquitoes built, fewer than 100 were shot down by German fighters. The 1.3% loss rate represented complete German failure to counter the threat. The lesson was permanent. In air combat, speed advantage of sufficient magnitude makes the faster aircraft effectively invulnerable to slower opponents. The Mosquito proved this lesson definitively. German pilots learned it painfully through repeated failure. British crews exploited it confidently through thousands of successful missions. When German pilots first chased Mosquitoes and realized they couldn't catch them, they confronted reality that no amount of courage, skill, or determination could overcome. The physics of pursuit when target speed exceeds interceptor speed. The thermodynamics of supercharger performance at altitude. The geometry of range closure rates. These weren't opinions or tactics or doctrines. These were mathematical facts. And mathematical facts don't care about German technical pride, or Nazi ideology, or Luftwaffe reputation. The Mosquito flew faster than Bf-109Gs at 27,000 feet. Therefore, Bf-109Gs couldn't catch Mosquitoes. The logic was absolute. The conclusion was inescapable. And German fighter pilots spent 3 years learning this lesson over and over until they finally stopped trying. That's what happened when German pilots first chased the Mosquito and realized they couldn't catch it. They learned that sometimes in war, engineering trumps everything else, and Britain had engineered an aircraft that German defenses simply couldn't counter.